In this lesson, we're going to talk about derivatives and rates of change. Back in lesson 2.1, we looked at this scenario where we had point P on a curve and point Q. We took Q to get closer and closer and closer to P, and we calculated the slopes of the secant lines between points P and Q, and we took that concept as a limit coming from the right and then also from the left. By doing so, we were able to calculate the slope of the tangent line to the curve at point P. Using that same concept of a limit, we have this first definition: the tangent line to the graph of f at point P, which is a comma f of a, is the line through P with this slope. So the slope is the limit as h goes to 0. In the numerator, we have f of a plus h minus f of a all over h. This first example says find an equation of the tangent line to the graph of f, which is the square root of x, specifically at the point 4, 2. So here's a diagram. We have the square root of x and we have the point 4, 2, and I drew a tangent line. So we want to find the equation of this tangent line. In order to find the equation of a tangent line, we need point and slope. We already have the point, so we need to find the slope. So in order to do so, we're going to use this formula for slope. We're going to go limit as h goes to 0, f of a plus h minus f of a all over h. And a is the x-coordinate of point P. I want to note right here it says f of a, so f of a is the y-coordinate of point P. So let's set this up. A is going to be 4. So I'm going to write the formula f of a plus h minus f of a all over h. Alright, so this is going to be your formula for slope. Let's go ahead and plug everything in, given that we have f is equal to the square root of x, and the point is 4, 2. Right here, when this says f of 4 plus h, that means we're going to take 4 plus h and we're going to plug it into our function f. And again, f of 4 is a y value, and it's specifically the y value when x is 4. So we look right here, the y coordinate when x is 4 is 2. At this point, to evaluate this limit from the last chapter, we're going to use our limit laws. So again, we take the conjugate of the numerator and we multiply that on top and bottom. So again, the trick to simplifying this is you're going to multiply out the conjugates either using distribution or FOIL, and then you're going to leave the non-conjugates as a product in the denominator. If you're going to FOIL the numerator, you're going to take this first term times this first term and you just get 4 plus h. When you multiply the outer and the inner, they're exact opposites, so they cancel out. And then finally, the last term times the last term makes -4. At this point, the 4's in the numerator cancel, and then at this point, the h's cancel. And finally, to evaluate this limit, we're going to take the limit of the numerator, the limit of the denominator. When we take the limit of the denominator, we're going to use the sum law, where we take the limit of the first term plus the limit of the second. And when you take the limit of the first term, you're going to pull the square root to the outside and take the limit of the inside function. So the limit of a constant is just the constant, so that happens here and here. And here we have a polynomial, so you can use direct substitution property. So for slope, you get 1/4. And finally, the problem wanted us to find the equation of a tangent line to the graph at the point 4, 2. So we're going to take this slope and we're going to use this point to write an equation of a tangent line. And I'm going to use point slope form so I can write that out for us. So our final answer is going to be y minus y1 is 2, slope is 1/4, and x minus 4. The last thing I want to point out is the slope of the tangent line that we got was 1/4. And if you look at this diagram, you can see that this slope right here of this line could easily be up 1 and over 4. So the answer that we got makes sense to the graph that we started with. In this example, it says find the equation of the tangent line to this curve at the point 3, 2. So the first thing I want to identify is the a value, and so the a value is going to be the x-coordinate, so a is going to be 3. Again, to find the equation of the tangent line to the curve, we need point and slope. We already have the point, and we need to find the slope. So we're going to set up the equation to find slope, and I'm plugging in 3 for a. So right here we have f of 3 plus h. So we're going to take 3 plus h and we're going to plug it in there and there into our original function. Next, we're going to subtract f of 3. So remember, f of 3 is the y-coordinate of our point P. Okay, at this point, in order to simplify this limit, first I want to simplify this fraction right here. So we can combine 3 minus 1, and we can also combine the 3 minus 2, and then I'm going to rewrite it as h and then the constant. At this point, to simplify this complex fraction, I want the numerator to be one fraction. So I'm going to put this 2 over 1, and we need a common denominator. So the common denominator of these two top fractions is going to be h plus 1. So what I'm going to do is I'm going to distribute this -2 to both the h and the 1. So now we have common denominators and we can add these two fractions. So when we go h plus -2h, we get -h. And then you can see that 2 plus -2 is going to cancel. Okay, so at this point we have one fraction divided by h. So I want to, instead of dividing by h, I want to multiply by its reciprocal. So again, right now this is divided by h, and if you want to think of it as h over 1, then we're multiplying by 1 over h, the reciprocal of just plain h. So now you can see that these h's are going to cancel, and you get the limit as h goes to 0 of this rational function. So now we can use the direct substitution property, and we can plug the 0 in for h. So we end up getting a slope of -1. Now that we have slope and we have a point, we can use the point-slope form to write the equation of the tangent line. So the equation of our tangent line is going to be y minus 2 equals slope times the quantity x minus 3. And here's the equation of our tangent line to this curve at the point 3, 2. Okay, next it says there is another common limit expression for finding the slope of a tangent line. And so we're using this formula right here. It says the slope of the tangent line to the curve f at the point a comma f of a is given to you in this form, slope equals. And this equation right here matches this diagram. We have a and then we have x, so two different x values. And it says the limit as x approaches a. So as we move x closer to a on the number line, it'll bring point Q closer to P. And if you take that limit as x goes to a of f of x minus f of a over x minus a, which again, this is just the slope of the secant line between these 2 points, concept of this limit where Q is getting closer and closer to P will give us the slope of the actual tangent line right at point P. This example says find the slope of the tangent line to the curve x cubed at the point -1, -1. So first I want to identify the a value, and again the a value is the x coordinate of the point. So a is -1. To find the slope, we're using the formula, the limit as x goes to a, where a is -1. Then it says f of x minus f of a. So f of x is just the function, f of a is just the y-coordinate of point P. So I plugged in the function, so this is f of x, we have x cubed minus, and then this right here is going to be the y-coordinate. So if you look at your point, the y-coordinate is -1. And then down here, it's supposed to be x minus a. A is also -1, so we're going to plug in -1 right here as well. So make sure you know the difference. Again, this is the y-coordinate of point P, and then right here, this is the a value of point P, or the x-coordinate. Okay, at this point, to evaluate this limit, this is a rational function, but if you use direct substitution property and you plug this -1 right in, you'll get 0 in the denominator, which can't happen. So we're going to manipulate this. In order to manipulate, we're going to factor the numerator using a sum of cubes. So remember, factoring using a sum of cubes, it goes little and a big parentheses, and then it goes a, b, this is a squared, then we multiply a and b together, but 1 times x is just x, and this is b squared, so 1 squared is 1. And then use the acronym SOAP. This is your sign that you're referencing, and you do SOAP, same, opposite, always positive. And now these x plus 1s cancel. And finally, this is a polynomial, so we can use the direct substitution property, and we're going to plug the -1 right in. So the slope of the tangent line is 3. So I have a note here. It says, suppose an object moves along a straight line following a position function f that describes the motion of the object. We have a formula for average velocity. So average velocity is displacement over time. So you can see that this is from the original diagram on the notes. You have change in y over change in x, and that simplifies to this. So this quotient is the same as the slope of the secant line between points P and Q. If we compute the average velocities over shorter and shorter time intervals, we will be letting h go to 0, and that gives you your limit down here. And finally, I wrote down that we can also refer to this as an average rate of change. Again, change in distance over change in time. Okay, so I put a little note. To find the average rate of change of a function f over a closed interval from a to b is going to be the formula f of b minus f of a over b minus a. So again, this is just slope of a secant line, and again, we refer to it also as average rate of change. So again, if you need the average rate of change formula, you're going to use this formula right here. All right, so all of this leads us to our next definition. We have velocity, or instantaneous velocity, noted as v of a, specifically when t equals a, is the limit of the average velocities. So you have v of a equals, and here's your formula for velocity. The limit as h goes to 0 of f of a plus h minus f of a all over h. This example says a particle moves along a straight line. For t greater or equal to 0, the position of the particle is given by s equals f of t, which equals t squared minus 5t, where s is measured in meters, t in seconds. Find the velocity of the particle when t equals 7. So you'll notice t equals a, so that means a is 7. So we're using the same notation. We're going to go v of 7 equals, the limit as h goes to 0, and then it's f of 7 plus h minus f of 7 all over h. We're going to take 7 plus h and we're going to plug it in for both of these t's. And then right here it says to subtract f of 7. So we're going to subtract, and then we just need to find f of 7. Okay, so f of 7 is 14. So next we're going to multiply this out. We're going to distribute this negative 5 and then combine like terms. To finish this, we're going to factor an h out of the numerator. These h's cancel. And we have a polynomial, so we're going to use the direct substitution property. We're going to plug 0 in. So our velocity when t equals 7 seconds is 9 meters per second. Thanks for watching, guys.